All right, so let's talk about cryptography because it's a big part of security, of course. And I go through a whole cryptography course where we talk about AES and RSA and elliptic curves and hash functions and all that jazz. But in practice, the best thing you can do if you just want to encrypt stuff is to use Sodium. Sodium is the library that was written just to make it easy for people to use good encryption without worrying about it very much. This is a library that will automatically choose the best algorithm and the right length of the private key and everything else. So you can do it in Python and you can read about the Sodium library and then um, you can read about the key derivation function. And now um, it's really very easy. You get a password, you encode it, and then you use it to calculate a key with a key derivation function. And that gives you a random key. And then you can encrypt a message with the Sodium secret box key to just encrypt it, and that'll give you random looking ciphertext. And then you can decrypt it if you have the key. And it's this kind of raw hexadecimal data is hard to transmit and store and all that. So what's common is to just encode it with base 64. So it turns into just a string of letters like this. And so you can do it that way. And so it's very easy to have ciphertext decrypted with that key to find the flag and decrypt it with a password. And there's some challenges here where you crack the password. This is all private key encryption, where you have a secret key and you have to somehow securely deliver the secret key to the person at the other end, which is a problem. So when you can't do that, you do public key encryption, and Sodium will automatically do this for you too. Bob generates a private key and a public key pair with just a generator function. And then Alice at the other end, Alice is going to talk to Bob. She generates public key and private key pairs. And then you send the messages back and forth. You publish the public key where the other person can see it. They encrypt something with the public key and send it to you with the private key. And you can decrypt it. And it only takes a few commands in Python. So this is the way to code with normal security. However, it is using the standard algorithms like elliptic curve cryptography and AES. And of course, the big issue now is quantum computing and the danger of that. Now, here's the fundamental fact about quantum computers. Quantum computers right now are not a risk, but if they get a million times better than they are now, then they'll be able to crack all public key encryption algorithms that we standardly use, RSA, elliptic curve, and discrete logarithms. All of them are shot, no matter how long you make the key. But the private key algorithms, it's only going to cause you to double the length of the key. So AES 128 may no longer be secure, but AES 256 will still be perfectly secure because even 100 bits is all you need. If you really had to do 2 to the 100 calculations, all the computers in the world running for all the time in the world could not do 2 to the 100 calculations. So if there's no shortcut, and you really have to do 2 to the 100 guesses to find the key, that's perfectly safe. And AES 256 would still require 2 to the 128 guesses even on a quantum computer. So private key encryption is fine, but private key encryption has this key distribution problem. You have to somehow deliver the key to the other end, so we use public key systems like RSA and ECC, and those are going to be shot. So we have to move to post-quantum cryptography. And the competition among mathematicians and companies to define the official government-approved post-quantum algorithms is still going on. It's been going on for about 5 years, but they have approved the first few algorithms. And so here you can learn how Kyber works. Kyber is one of the first ones that was approved, and Kyber uses lattice cryptography. And so the mathematics can get pretty confusing, more complicated than RSA, which is pretty simple. So you have vectors of polynomials, and so your private key is a polynomial with small numbers like this. There's like 2 polynomials of third order with coefficients of plus and minus 1. This is of course, a insecure, very small system. The secure one would have much longer polynomials and larger coefficients. Then you need a modulus. You generate a matrix of random polynomials, and then you add errors. And then you calculate a t by doing a matrix multiplication in polynomials and adding the errors. So you end up with, then you make them modulus here so that the power is limited. So the math gets a little complicated, although it's nothing more than algebra. And you end up with this quantity t. And now t is part of the public key. A and t together form the public key. And the private key is the small errors that were, a small polynomial of small values that was included in there. So here's what the public key looks like, A and T, and that's the private key. And you can encrypt things with this stuff called lattice encryption. Now, it's called lattice encryption because this is mathematically related to another problem. In fact, let me see if I can find a good example of lattice encryptions here. I didn't put it in this project where it might actually be helpful because it's not obvious, but the lattice problem is actually kind of easy to understand. Let me see if I can find a good picture for it. Um, let's try going to images. There we are. These are pretty good pictures. That's what I wanted to show you. All right. So what happens is you have a lattice, which is a grid of points, and you can consider that grid of points to be created from generating vectors. Like you could use just B1 and B2, and then it would be a combination. To move from this point to any other point on the lattice, you'd have some integral mixture of B1 and B2. And if you try to calculate what is the minimum number of steps to get to a certain point, or to indeed to get to the lattice point nearest to a point that's not in the lattice, those are the very hard problems in general, especially in many dimensions in a big lattice. How do you combine these vectors to reach a point, and how do you find the point that's nearest a point here in terms of how many vectors are added? That's the lattice encryption problem. And remember, you also add some random noise to it when sending it up, and that helps hide it too. So that's the fundamental hand-waving way it goes. And you can actually go through all this and calculate all these parameters to get some clue of what math is behind it. But most people, most engineer types that are trying to build a website or something, they don't really understand or care about this detail of the math. They want to just use it. And that turns out to be very easy. As it should be, right? Once they get their ducks in a row, you'll just turn on a module of code somebody else wrote and not worry about the internal details too much. So you can take your web server that you set up for the previous projects and turn it into an HTTPS server. Now, the problem is it has to have a domain name, and the domain name would have to be registered with DNS if you wanted to make it publicly available. But what you can do is you can just put it in your local hosts file. So choose a domain name. This way you avoid spending any money. Put it in your hosts file like this, and now your one machine will be able to find it from the domain name. Okay, then you can go to that domain name and reach your server with HTTP because it's just running Apache. Now all you have to do is generate a self-signed certificate, which is just a couple commands with and then install the certificate into Apache and enter a configuration file that tells it to serve on port 443 encrypted data using the certificate. It's only a few lines of code, as you can see. And then you'll be able to open your page with HTTPS. Now, the browser will warn you that the certificate is not approved by a certificate authority because you didn't pay for a real public domain name and a real public certificate, although those are free from Let's Encrypt now. So all you'd have to pay for is a public domain name, but you would have to pay for that. Those are not free. And anyway, but you can click through the warnings to get there and you'll see the page. And then you can use Wireshark to examine the handshake. And if you use Chrome, and connect to your server, the client hello message as part of the HTTPS handshake will show the cipher suites that are available. And you'll see a bunch of them, and I picked one of them to be a flag, one that's sort of a test suite that's used. But you have a lot of different encryption algorithms that are allowed here. So this is ordinary HTTPS using the ordinary old-fashioned encryption routines like RSA and elliptic curve cryptography, which, as I say, are going away. So the next step is to upgrade your server to use post-quantum cryptography, which you can do. You can go into Chrome Developer Tools and you can turn on more secure encryption. All this is an optional feature in Chrome, but you can encrypt stuff. Right now, it's encrypting with an elliptic curve protocol. And you can examine the handshake and you'll see what's used here. Now, your server hello will have this stuff in it. All right, and now you can add post-quantum encryption to your server with OpenSSL you install some software, which you get from Open Quantum Safe. OQS provider got Git. You can get this stuff, run scripts, and you can then configure it on your server. Adding this stuff to the quantum safe and going to providers and adjusting the algorithms. And then you turn on this thing, X25519 ML-Chem. This is, I think, Kyber, ML-Chem. And what this does actually, which is probably a pretty good idea during the transition period, is it uses both the old-fashioned elliptic curve algorithm and the modern post-quantum encryption. This is a good idea. When you have a new kind of encryption you might not be able to test, you don't just thoroughly test the new one, you add the old one and the new one together. So only when they are both broken will you be broken. That's the idea. So you add that here and add it to your Apache configuration file. This is one of your Apache configuration files. You now tell it to use these SSL in post-quantum encryption. And then you can reload your page in Chrome, and now you'll be able to see that it in fact is, I wonder if there's something wrong with this picture. But anyway, you should be able to see X25519 here. And there it is, X25519. So it is now encrypted with post-quantum encryption. So it's not too hard to set up, and we're all going to have to get used to these terms and seeing them go by. This is what everybody should do within maybe the next 5 or 10 years to be prepared for the onset of quantum computers. All right, and that's all I have at this point. So I'm going to stop this video. I'll be adding more of these as they approve more algorithms.